Now we have material with the composition and the property we want to predict, like this. These data are cleaned using previous step, like data cleaning. This composition and the property we want to predict is listed like this in a CSV file. We need to then create a composition based feature vector. These are the formula and the 2D plasma frequency like this. For that, we need to, for training, we need to make composition based feature vector. So how to generate composition based feature vector? There are several different featureization schemes available. So in this Python package CBFP, we can easily do the featureization using the Python package. So one of the featureization scheme is Olinik. For that, for example, we have the formula AL2O3. We will normalize the number 2 and 3 to 1, total 1. Then we will make a feature vector like atomic number times the normalization plus next element, like this. A big feature vector will be generated. This feature vector can be used for training our machine learning model. To train our model in the training and validation set, you'll go to the folder second. You can see here there are many Python Jupyter notebooks here. These are all Jupyter notebook I made for different material predictions, property prediction, like 2D plasma frequency, x direction, y direction, area, all. For example, here I will be opening 2D plasma frequency, x direction. Well, these are all same, like only little code is different. So first, in the Google Colab, we need to uncomment this and run the cell. I have already run this and saved here, so you need to run the cell. So it will install the CBFP package into Google Colab. If you are using on your local device, you only need to install the package first time. Then we will import OS, pandas SPD, numbers NB, matplotlib. Matplotlib let you plot the graphs and prediction, linear prediction, etc. So this is the sklearn is the machine learning library we are using for prediction of classical machine learning. So from the sklearn, we will import train test split. It will split the data into training and testing set. We can run the training test function again to create a validation set. So if you have a original data like this, we can select random rows like this, and then we will get about 90% training data and 10% testing data. We can split the training data again to create training data and validation data. If our data which is bigger, we may need to use validation set, which will help to find the best machine learning model faster without training entire data. So in the Google Colab, we need to run the cells by removing this comment, which will mount. So the path here is in data C62 dB 2D plasma frequency X CSV file I showed you earlier. So here this path is for local computer, that's why dot. You need to change appropriate path for your system. Like after mounting, you need to change the path like in the previous tutorial I showed you. So it will be load like this, formula and the 2D plasma frequency. This is our training data. So to generate composition based feature vector, we will install this package like this. To run the package, you need to change the heading of, for example, formula and 2D plasma frequency to formula and y, formula and target, sorry. So using this code, we can change, then rename the column headings of the data frame. Here we are importing several different classical machine learning algorithms for our prediction. We will train our data on the validation set. Training on the validation set validation set is smaller, so it will let you train the model faster. You don't need to train the uh, entire model on the training set. So here we are importing dummy regressor, ridge, ADA boost regressor, extractive regressor, like this, all machine learning models. All these are the model we are importing. The dummy regressor is just a dummy, which is not a model. If our model performing worse than dummy regressor, something wrong with our data, or you messed up something in the code. So these are the metrics we are using to evaluate our accuracy of the prediction. R-square value, mean absolute error, mean squared error. So these are the functions that we will use to partially train our model. Like this function will take the model name and output model, and this fit underscore model will take model name, x train, y train. X train is input, x is that formula and the composition based feature vector, and y train is the property we want to predict. Then this is how in the fit model we will fit using model.fit command. This time minus ti will let you know the amount of time it required to train this particular model. So this is the evaluate model, which will check model evaluation metrics like R-square value, mean absolute error, using these commands. So the fit evaluate model function will call all these functions above and train the model. These are the result dictionary we are making for the data frame, where we will store our results, so later we can see which model performing better. This is the function to append each results into the dictionary that we have created. This is the function to plot our prediction, like actual values on the x-axis, predicted values on the y-axis, to see how good our machine learning model is performing. Here, like, we are plotting using matplotlib. So these are the command. You can look up the matplotlib official website to see what these are doing, like this orange plot, orange line, axis, x label, y label, title of the plot. So these are the dictionary. These are the machine learning algorithm that we are using. We just give the short name for representing in the data frame. So these are the all composition based feature vectors that are available on the CPFP package. There are this MACPy, MATVEC. So essentially what we are doing is we are training them each different machine learning model with all these featureization scheme on the given data to find the best model and best featureization scheme for the validation data. So it's in the featureization, we will make the featureization using this command train underscore split. We are splitting the data using train underscore test underscore split. First time to create training data, and second time splitting again to create the testing data. Validation. First time to create the testing data, second time to create the validation data. So here seed is 42, we can change the seed is here for the reproducibility our data. Next, we need to uh, fit and transform our input data, because there will be like some of the input will be very minus 200, and our next line will be plus 230. So we need to scale the entire data between 1 and 0, so our machine learning algorithm will not get lost in the number. We just need to know the trend in the input data. So we will fit and transform our input data. So we are this is the function we are calling to keep track of time. We are looping through each model, fit and predict, evaluate the model and store the result on the dictionary. We are calling this function fit underscore evaluate underscore model, this function in the top, this function. So this will print, this line will print the amount of time it requires to train the model. So we are plotting on the validation set, you can see. So these are the results, you can see. These are training. If you run, it will take some time. So these are the already run results I'm showing. As expected, the dummy regressor is not performing good. So with checking which is the best model, I already checked. So the best model is best featureization scheme is Olining, and best machine learning model is extractive regressor. For this particular input data, we have given 2D plasma frequency in x direction. So Olining. See, the Olining extractive regressor model performed better than any other model with a R square value 0.6806. Ignore this I forgot to remove. So for the featureization scheme, we now know Olining perform better in the validation set. Now we will train with Olining model only in the entire data again to find the best machine learning or classical machine learning algorithm. We now already know it is extractive regressor, but we will train again to confirm it with only Olining this time. So I already told you why we need to scale the data, fit and scale. Here why we are fit transform and scaling, why we are doing scaling. So this is the unscaled value. You can see the atomic number is like this, and atomic weight is 400. The this sum underscore non-metal, this value is like 444. So our machine learning model may lost in the details, so we don't want that. We can scale the entire row between 1 and 0 and 1. Also we can scale entire column in 1 and 0, so it will make the machine learning model easy to train. So we are using like previous time. Again we are splitting the data in the training and testing test using sklearn function train underscore test underscore split. For like this is the usual percentage of splitting data we do in machine learning. There are different data scaling normalization schemes available. We are here using standard scaler. Again, these are the machine learning classical models we are importing from a scaler. We can also import other model. Again, same. So this is the result dictionary I talked about. Dummy regressor, linear receiver, data booster. These are sorted in the order of increasing R-square value. You can see extractive regressor performed better with the R-square value perfect 1. 1 is the maximum value in the training set. We are interested in the validation set with a maximum R-square value of 0.6658 in the validation set, and mean absolute error and root mean square error respectively. So from this table we know extractive regressor and Oleaning featureization scheme perform better on the validation set. So to plot the our data, we will use the again plot function, and you can see random forest only 0.62 and extractive regressor with R-square value fitting of 0.6658. So for this given 2D plasma frequency X direction, Oleaning featureization scheme and extractive regressor is the best choice for the validation set. In the next tutorial, we will see how we can do this same thing in the testing set, and we will do hyperparameter tuning or testing set to improve the accuracy of the prediction, like improve the R-square value. Here, this is the actual value and this is the predicted value. The dashed line is what we want. This is the ideal case. 45-degree line. If all the points are in 45-degree line, our predictions are really good. I will show you one ideal prediction. I think in energy prediction, or almost all the data fall on the 45-degree line. The prediction is good with R-square value 0.9024. This can be improved after hyperparameter tuning. If I remember correctly, sorry, the best model is reached. The R-square value is 0.9918. This can be also improved with after hyperparameter tuning. So these are all the predictions I have done on the validation set. These are the properties I have predicted. These are the best featureization scheme. Almost all is Oleaning. Some of them is Jarvis and McPy. Best classical machine learning model is static regressor, gradient regressor, ridge regressor, etc. This is extra-tree classifier. R square value, mean absolute error, and root mean square error. These are the plots of prediction that we are doing. Here you can see for this one, thermodynamic stability level is a three value like 1, 2, and 3. This stable, more stable, and most stable. So we cannot do the regression here. We need to do the classification algorithm here. That's why we are using extra-tree classifier here. Otherwise, you can see these are the continuous values and these are discrete values. Otherwise, all the processes are same. Instead of giving classical regression algorithm, we will do classical classifier algorithm.